Okay, everybody. Hello. Sorry, I'm late. I should have gotten over here a little bit sooner. Thank you for your patience. So, oh, there's nothing on the screen though, huh? You want to see something here? Let's do this. Okay. And that's one end. Okay. So, the last time we met, we discussed torsion again, right? So, we had, let's see, this is going to be whoa, what's going on? Okay. So last time in session 10, sorry, we discussed torsion, right? So we had session 10 last time. And some of the things we discussed were shear strain, shear modulus, angle of twist, indeterminate loading, and we also discussed relationships between torque, stress, and supportable load. Okay, and so if you look back at your notes, you'll probably see some things kind of like this, where we had shear strain being induced by shear stress. We had a matrix formulation to go from stresses to strains, both normal stresses and shear strains. And we also discussed indeterminate loading. We also discussed distributed loading too, and how to handle that. So today what we're going to do is briefly discuss logistics for the exam. And then we'll get into more torsion, but using FEA. And then the bulk, I think, of our time will be spent discussing beams. All right, but just the very beginning of this. So beams and graphical methods for plotting shear forces and bending moments. Okay. So some of the things that we hopefully will be able to do, so by the end of today, okay, we should be able to do the following types of things in mechanics. Okay. We should be able to calculate internal bending moment, all right, with transverse loading. So internal bending moment, and you already can do this with what you know from statics. We should be able to calculate internal shear forces, which you should also know how to do from statics. We will have relationships between transverse shear forces, okay, and distributed loads. Okay, so that will probably be a little bit new. And similarly, we'll have a relationship between transverse shear force and bending moments. Okay. So, spoiler alert. Okay, this one is going to look like dv dx is equal to w, or omega, however you want to look at it. Okay, and this one is going to look like dm dx is equal to v. Okay, so we'll derive these relationships. Okay, so that's kind of an overview of what we should be covering today. Any questions as we get going here? Okay, so first, you already probably saw the message about exam 1 or the multiple messages, but we're meeting here. It's on Friday, normal time, and please bring a calculator, and please bring a sheet of notes, front and back, and handwritten. Okay? Any questions? Okay, good. There was the question of what to study. You should be able to do. What's that? Oh, sorry. Thank you. That's because I copied, right, from a past slide. Yes, do not show up here on October 17th. Thank you. So February 24th. Okay, thank you. Yeah, in terms of what to study, you should be able to do any of the problems based on the notes. What I typically do, well, sometimes I do, I look through the notes and I see things and then I pick things and then I make the problems off the notes. Okay? Also, the assignments, okay, should be helpful. For example, we did some problems with gears. I'm not leaning toward putting a problem with gears on this exam, all right, but it's something we covered. Okay. All right, so the next thing on the agenda, let's look at some finite element for a problem that maybe some of you have already started doing. Okay, so this is a very rough transmission, okay, going from one gear to another gear to a drive axle. Okay, so I'm sure some of you are more into cars than I am, all right, but often you have the engine and you have a transmission, okay, there, and you're going from high RPMs with low torque to lower RPMs, higher torque, to a drive shaft. Okay, so sometimes that drive shaft will run underneath the car if it's, for example, if the engine's in the front and it's a rear-wheel drive truck or a car, right? So that would be a drive shaft. And then it goes to a differential, okay, and it splits out, and you have drive axles, okay, going to either of the wheels or to both wheels, okay. And so here, let's just imagine that we have a 10 kilonewton force pushing the car up a hill or accelerating it down the road, okay, or battling wind resistance. Okay, but we have a 10 kilonewton load that's being applied horizontally to the vehicle. Now, that 10 kilonewtons is being split between two driving tires. So this is not a four-wheel drive vehicle, this is a two-wheel drive vehicle, we'll say. Maybe it's even a three-wheeler. I don't know, but we're just looking at the driving wheels for this system. Okay, so the force is split equally between the two. Okay, so with the force split between them, it then goes into the wheel, and these wheels are 56 centimeter diameter wheels. Okay, and that's like not too abnormal for a regular size car. Okay, somewhere between 55, 57 centimeters, something like that. And then those wheels are connected to this drive axle, this shaft, which has a different radius, a radius R3. You're like, hey, why don't I make it the same radius? Well, I want to save material, and I don't want all that inertia there. Okay, so we're going to use a smaller shaft, right, than I have with the tires. So here's some of the parameters. We have a wheel radius of 23 centimeters. We have the length of this axle designated as 1 meter. Okay, so that's not too abnormal. The average car has kind of a width somewhere between like 5 and 9 feet. Like 8 foot would be a truck. Okay, so and 5.5 feet might be like a little sedan or something like that. So 1 meter, and we're going to say it has steel as its material, so 200 gigapascals and a Poisson ratio of 0.3. Okay, so what we really are interested in is understanding what's happening on this drive axle, and so that's what we're going to model. So we bring up our FreeCAD, and we're going to make a cylinder. Okay, and that cylinder is going to have length of 1 meter and a radius of 3 centimeters is what we've decided here. Okay, whoa, so we'll go ahead and create new, and we'll come over here and we'll use part, and we will create a cylinder like that, and here we're going to say the radius is 3 centimeters, okay, and the height is just going to be 1 meter. Okay, and so you can see that we've kind of made it much larger than it was originally intended to be, or originally was. Okay, so there you go. And then we can come over here and we can go to part design, which is more similar to what you might find in your conventional 3D modeling packages. We come over here, we do a transform, and I've set it, I think the default is 15. I guess it remembered that I wanted 90 degrees, and I'm just going to rotate this down, okay, like that. So now we have, for better or worse, our shaft, okay, move this, is aligned with the x-axis here. Okay, you could have done it, we could have done it with a Z. It doesn't really matter. So we will go ahead, and I won't even bother to save it, but I will make sure I export it because I need to bring it in to, okay, so I already have a drive axle, you can see, all right, but we'll just save over that. Okay, do you want to replace it? Sure, and it's going to be on the wonderful desktop. Okay, so now I'm going to go in and I'm going to find my prepo max, which I've extracted previously. Okay. And it's just, it doesn't even install, you just open it up. Once it's extracted. And what we'll do is we'll bring in our geometry. Okay, so we go File, we're going to do New, and we can go ahead and put in meters, kilograms, seconds, Celsius. Okay, we will go ahead and now do an import. Whoops, that's export, import, and I left it on the desktop. Okay, so there it is. That's it. That's the file. Similarly to what we had last time, this comes in. It comes in much larger than it should be, right? So we said the shaft would be 1 meter. This time it's 1,000 meters. So we're going to go ahead and we're going to scale the geometry. Do a transform, scale, and we'll just make this 0.001, 0.001, 0.001. Okay, and apply. Okay, so close, and it's disappeared, but we can zoom to fit, and then it shows up again. Okay, like that. So this problem is a little bit different than what we did last time, and the last time being when we did axial loading, and it's length to width ratio. It's a little bit longer versus its width, and that can sometimes lead to issues with meshing. So you don't necessarily have to do this, and when I assign one for homework, I'll try not to make it so that you have to mess with this too much. But here, I'm going to change the max size of my element, okay, to 8 millimeters. Okay, and then I'm actually going to say we can do, let's see what I do. Yeah, three elements per curvature. Okay, and then we can take a look and preview. Okay, and that doesn't look so bad. Okay, that's going to discretize this. Okay, with these points as being nodes. So we'll hit OK, and then we'll do the mesh. And this will take, whoops, okay, got it. Okay, so there. You can see it's kind of nice, beautiful setup mesh. It's not that beautiful, actually. You can see there's some irregularities to it, but for our purposes, it's fine. Okay, so now, one thing that we're going to want to do is apply a moment or a torque to the system, right? Last time we were applying an axial, actually we were applying pressure the last time. And we could have used this technique that we were going to do to apply a point load of force, okay, instead of distributing it over the nodes, but this time we really do need to use a different construct when we're applying this load. It turns out that the nodes in calculus, they cannot handle the direct application of a moment. So what we do is we fix a rigid surface or rigid body to these nodes, and then to that rigid body we apply the moment, and that's what applies the torque to the whole shaft. Okay, so to do that, what we're going to do is create a reference point. Okay, so this is going to be the reference point where we apply the torque. Okay, and that's going to come out. I just knew the dimensions. I knew it was 1 meter, right? So I put it at, and the x-axis is going right through the middle, so that's convenient. So it's at 100. And then we're going to introduce a constraint, okay, a rigid body constraint, and it's going to go to the reference point. See, it's already put it in, and we're going to connect it to the surface, and we're going to connect it to this surface right here. Okay, so it should just be, yep, just that surface. Okay, so okay, and now that point has been connected to a rigid body, which has been connected to the structure. So let's do the other things that we need to do. We need to set the materials or set a material, and it's going to be elastic, and we're just going to call steel with a elastic modulus of 200 gigapascals and a Poisson's ratio of 0.3. Okay. We are going to create a section that's just selecting the entire body, which is that. I think that should have worked. Sometimes it's hard. Yep, see, now I know it's selected the whole thing. So, okay. All right. And now, another thing that's going to be a little bit different. First we got to create the static step. Okay. Another thing that's going to be a little bit different is we want to know the angle of twist, and so Prepo Max has a nice way of handling the motion of selected points. So we have this reference point, and we want to know how it's rotating. Okay, it's not really going to be, there's not going to be elongation in this system, not significant at least. Okay. So what we can do is we can go to this history, and we can create a history, and we're going to look at a node output and the variable. Okay, so it's going to be a node output, and the variable is going to be u. Okay, and u is essentially a column vector which describes XYZ displacement and rotation in about X, Y, and Z. Okay, you probably don't care that much, but it'll become apparent in a minute. Okay, now we want to apply our boundary conditions. Okay, so we'll create a fixed boundary condition on this side. Okay, and then we want to do a load. Okay, and we're going to do a moment, and we're going to do a selection, right? Again, our reference point. And which direction, right, are we applying our moment? We're applying it about X. Okay, so now we're going to do that. And now I'm going to go back to the PowerPoint real quick, okay? So I had to calculate out what the torque is going to be on this shaft, okay? The torque is calculated by looking at that force divided by 2, right? That's the force here, okay? And then it's being applied at a distance r4 from the center of the shaft, okay? Even though the diameter is smaller, right? They're connected to each other, they're coupled with each other, and so the amount of torque that the shaft is interested in seeing, or that we're interested in seeing, is given by the r4 radius. So the torque comes out to be 1150 Newton meters. So where are we? Here we go. Right. So we're going to apply a torque 1150 Newton meters. We're going to hit OK. All right. Now, moment of hope. We run. Okay, took a little bit longer than I was expecting, 8.5 seconds. We look at the results, and what do we see? Well, we see a rainbow. Isn't that so nice? Red, orange, yellow, green. Okay, blue. Roy G. Biv, right? Okay. So, but that's that's not necessarily what we're interested in. This is just the displacement, and this is talking about kind of an XYZ type of displacement. All right, and if we look, there is some, but it's not that significant. So what would be the two things that are interest to us? If you're designing this drive shaft, or this drive axle, sorry, what do you want to make sure is happening or not happening? Yes?
Like it doesn't bend off.
Okay, so it doesn't bend off. Okay, it doesn't shear off. All right, yes. Okay. And so what do you suggest that we do? What is our test for that? Yes.
Minimize angle of twist.
Say that again?
Minimize angle of twist.
Okay. You could minimize angle of twist. All right. And yes, there's going to be some connection, right? Because you're like, oh, if there's a huge angle of twist, that could potentially have a large shear strain associated with it, which could have a large shear stress, right? So in terms of evaluating whether or not something's going to fail, right, we want to first make a comparison to the yield strength of the material or the shear strength of the material as we have here. Now, we didn't specify what that shear strength might be, okay, here. Okay, so, we could do a design problem and say, okay, you must make it so that the material does not have shear stress greater than, I don't know, 200 megapascals. Okay, that's probably a reasonable amount. And we'll get into how, we already actually kind of discussed how shear strength is half of yield strength, right? So 400 megapascals is a pretty high yield strength for a material, okay? It's not out of the range of what you can do with steels, but it's pretty high, okay? So let's take a look. Let's take a look at what the shear stress might be. Now, you see over here some S11, S22, S33, okay, S13, S12, S23, or something like that. Yeah, those combinations, right? If we're interested in shear stress, okay, which ones are the most relevant? Now, this is a little bit of a tricky question. I think it's a little tricky, okay? Which ones are we most interested in? So let's maybe do a process of elimination game. Okay? Are we interested in S11? Anyone say no, right? That's an axial, sigma x, right? Not very interesting. Similarly, sigma y, sigma z, so S22, S33, right? Not particularly interesting in this case, okay? And if we look, right, S11, okay, yeah, it has some values, okay? But this is essentially 500 kilopascals, okay? That's really small when it comes to stresses, okay? Or pretty small, depends on the material, okay? So we can see that S11, S22, S33, not very interesting. Okay. So that leaves, right, the 1, 2, 1, 3, 2, 3. Okay, so when we think of shear stresses and we take a cut and we're looking at the cut, okay, and this is coming off a particular axis, which face is that we're looking at? We're looking at the one face, right? We're looking at the X face, right? So I'm looking at the one face, it's coming, it's, looking at me, and I want shear stress. So which components am I going to be interested in? Yes, so someone's saying, you're going to be interested in this, if this is coming at you, you're going to be interested in this direction. Okay, and if that's Z, that'd be a 1-3 stress. Okay, and if I'm interested in this direction, the Y, right, that'd be a 1-2. So S12 and S13 are going to be the most important ones here. Okay, now, the other tricky thing is, I think maybe it is worth me just drawing a picture of this. Okay. Whoa, what is this? Okay, let's do. Okay, so we have this wonderful face, okay? And this is the x-axis, right? So remember, if we were to draw like a line through it, what happened? We had very large stress near the outside, right? And very small stress in the middle, right? Because what is this? This is tau is equal to TC over J for max, or T rho over J, right? Or T rho over J. Okay? So if this is X, okay, coming out, and this is Y, all right, or actually we'll say this is Z, okay, and this is Y. That's not a right-handed rule, so that's not a right-handed system. There, okay, is that good? So that's a right-handed system, right? So if we're looking at the face, okay, and this is Y and this is Z, okay, the maximum out here, which direction, which shear stress is that? The one I just drew. What would you give as subscripts here? This is tau. What's that? Yeah. Tau 1, 3, tau x, z. Okay. So that one's going to be tau x, z, or tau 1, 3. Good. So I think you're getting the hang of this. This one over here, right? That one would be tau 1, 2, all right, or tau 1 minus 2, but minus 2 is going to be the same as 1, 2, right? Okay, so we're interested in seeing these stresses be a maximum at the outside of the shaft, okay, at the top and bottom for the 1, 2, and at the left and right sides for the 1, 3. Okay? And then it will do something kind of interesting in between. So if we go to our system now, suspense. Let's look at, well, what do you want to look at first? Let's look at 1, 2. Whew, all right. What do we see? We see some interesting stuff, okay? And it's hard for me to control everything. Okay, so if we're looking at 1, 2, okay, so 1, 2, remember if we go back, 1, 2 would be on top as defined by Z and going off this direction. Okay, so let's come back over here. Okay, and let's, oh, this is, the brightness here is actually really hard for me to see. How do I control the brightness? Oh well, okay, I'll make,
Click the Wi-Fi.
yeah, all right. I can, well, you guys can see, you all can see. Okay, so what I'm going to do, actually, I'm going to do view, and I'm going to do a standard view, and let's see if we do a front view. Oh, not that one. Actually, that one's not bad. Okay, and I'm going to get rid of this. Actually, I'm going to get rid of this displacement here. Oops. Okay, I'm trying hard. Okay, you see this is the Z direction, the way that one came out. So the highs and the lows are going to be over here and over here. And I can't see diddly there. Okay, but let's just go ahead and let's select. Let's do a query somewhere over here. Okay, now what's that value? That value is minus 2.7 times 10 to the 7 pascals. So that's what, 27 megapascals. So if we go back to our calculations, what do we get? Bing, 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 bing. we got tau is equal to 27 megapascals. All right. So that is shown with tau 1, 2. Similarly, if we go back to pre-po max and we look at now the tau 1, 3, okay, things have now shifted so that this is the y direction. So now we're looking at the top. And if I do a query over here somewhere, what do we see? Once again, we see 2.76. All right, we see in the ballpark of 27 megapascals. Okay, this is pretty cool. All right, we were able to solve this problem here. Now, note, if I want to calculate out, first, before we do this, let's also look at the angle of twist. So we can come down here to our histories, and we said we wanted a u, and it was the displacements, okay, for that point that we had put out here, okay, and we're going to be interested in rotation. So that's going to be UR1, okay. And what does this come out to be? This comes out to be 0.012 radians. You probably can't see that, okay? But it's 0.012 radians. If we look, okay, at our calculations, okay, for the angle of twist, all right, just using TL over JG, all right, what we got was 0.012 radians or 0.67 degrees. Okay, so once again, we're able to use the software to agree with what we have. Now, here is something that will confound you if you're not careful. Let's say that we want to look at the strain, okay? And we know, so one way to calculate the shear strain is to say, rho d phi dz, okay? And I know my phi is 0.012 radians, and I know my L, my length, my phi at the end is 1 meter, okay? I know my radius is 3 centimeters, okay? So rho d phi dz there would just be 0.03 centimeters times 0.012 radians divided by 1 meter. Maybe I should write that out. Okay, so another way to look at this, right, is to say, okay, I'm interested in gamma, and that's going to be rho d phi dz, okay? And in our case, we said that was 0.01, oops, no. It is 0.03 meters, okay, because it's 3 centimeters. D phi, so the length, over the whole length, it was, we know that the ratio d phi dz doesn't change, okay, as long as you haven't applied different loads to the system. So we said that it was like 0.012 radians, okay, and that's over a length of 1 meters, okay. And so what does this come out to be? This comes out to be, according to my calculations from before, 352 microradians. Okay. So let's take a look. All right. So that's gamma, and we'll just go back, and we're already queried at a couple of spots, right? We see this spot. This spot we don't like too much because it's not giving us what we want. But let's just look at right here. Actually, no, that is giving us what we want. See, right? Just this is the point, or one of the points. Here, right now we're looking at sigma 1,3. All right, sigma xz, and it's a maximum on this side, but it's much smaller on this side, right? That's an orthogonal to it. But if I flip back to sigma 1 can't see anything. Sigma 1, 2, where is it? Oops, I'm going to close this. Sigma 1, 2, it flips. Then this one is high and this one is low. Okay. So now if we go, let's go ahead and we take a look at the strain. And let's say that we look at epsilon 1, 2. Okay. So S12, right? It was maximum over here, so we expect to see maximum strain over here too. Epsilon 1, 2. What do we see? We see 178. So I'm just going to write it down. We saw 178 microrad. Okay. Okay. That is not the same value we got here. And that is confusing. But it's like almost exactly half. So what's going on? What's going on? Well, we won't get into the details here, okay? But it turns out that there is a relationship between these epsilon xy, yx, and say gamma xy, and these epsilons end up being half of the gammas. This has to do with the fact that these are called tensor strains, okay, and these are called like regular true strains. Okay. For the tensor math to work out, there needs to be a half. And when we do something with more circle, we'll see that we have to use a half, a factor of 1/2 when we're doing these transformations. Okay, so don't worry about it now, but just be aware that if you're going off of the output of pre-pro max, which is dealing with tensor strains, that this conversion needs to happen. Notice we didn't have to do this when we were doing the axial loading last time, because epsilon xx and epsilon x, the main diagonals, those end up being the same. Similarly, the stresses also work out. Okay, so it's a 1-for-1. It's only with these shear strains that we have to be careful. Okay, so on an assignment, you'll get an opportunity to put a beam in the pre-pro max, or put it into FreeCAD, put it into pre-pro max, and then please, when you take the screenshots of your result, and if we ask for shear stress, then do a query, right, on an element, show the value, show that we're, doing S12 or S, make sure it's clear that element is showing the particular quantity, whether it be shear stress or shear strain or rotational displacement. Okay. Cool. All right, let's now move on to talking about beams and beam bending. But any questions, any thoughts, concerns? Okay. So some of today will be a review when it comes to the beam bending. Let's move this back up. Okay. So here we go, beams. What is the definition of a beam for this class? What do you all think? What is the definition of a beam? Or what do you remember? What is a beam, really? To beam or not to beam? That is the question. Yes.
Has like transverse loading.
Okay, so we're dealing with transverse loading, right? Okay, so that's good. That's a good point. So we're interested in transverse. Whoops. Yep. Okay. So that's cool. What else? What would be another characteristic? Yes? Okay, typically, yes, they're straight until we load them, right? But we assume that they stay pretty much straight. That's a good point, okay? So they're kind of straightish. And I'm going to elaborate there and say that they're slender. Okay? So their lateral dimensions are small compared to their length, right? So their width and height are much, much less than their length. Okay. And if we think of the internal loads that we're thinking about, right? If we have, this kind of cross section, and we draw the forces. We say, okay, well, let's say that there's like an Fx. Okay, let's say that there's an Fy or an Fxy, right, coming out, and let's say that there's then a Fxz. We see that we have an axial force, right? And we have two shear forces. Okay. If we then also think about the bending moments, or they're not all bending moments, the moments that we could apply here, right? We could see, okay, I'm going to put something coming out this way, and maybe I call that mx. And I could have said fxx as well, right? But we say, okay, we have an mx. Let's say that we have this is going to have the same subscript, right, as this force. So this is going to be mxz. And then let's say that there's a mxy as well. Okay, so which one is most related to torsion, like we've been discussing on shafts? Okay, we've done circular shafts. We have not done rectangular ones. Okay. Things change a little bit, but the twisting would be the mx, right? So we have a twisting moment, which would be mx, and then we have our bending moments. All right. And typically we're not bending into or out of the page, right? We're interested in how the bending moments induce curvature up or down, right? About the Z, if we call Z coming out of the board. Okay. Another characteristic of a beam, right, is that we have supports. We have to, the beams can't just be floating in space. Or, well, we can think of them when we draw reaction forces. I guess we think of them as floating in space, but we have supports for these beams as well. And so the typical supports that we will see, and there can be others, but these are kind of the main ones. Are those three, right? And we often associate the pinned one as being able to provide both horizontal and vertical restraint. The roller can provide vertical constraint, and the fixed, it does both vertical, horizontal, and axial. Okay, into the band. It's fixed and it does the moment as well. Okay, like that. All right. Now, let's go over the sign conventions real quick. Okay. So, if we take a cut, something just happened. My computer is not happy with me. I just did something. It's like suddenly working hard. Not quite sure why. That's not good. Okay, there we go. Okay. So, sign conventions. If we have an exposed face, right, what we typically do is we say that's going to be positive in that direction, and we're going to define forces as coming out for axial loading. Okay. And we'll say that's y. Okay. And if we had it facing the other direction, we call that x, and we have a force F. Okay, and this is y. Okay. We're going to say that we have a positive force when in the same direction. Right? Okay. If we have a moment, okay, we typically will say that if it's causing the beam, we think it's causing the beam to smile, right? That's going to be a positive moment. So similarly, okay, that's what you have. So it's plus m when in plus z, right? So you can see in both of these cases, right, the z is in or out of the page. And in this case, if y is up in all cases, right, it's coming out. Okay, that's going to be z. And this is going to be in. Okay, so that these are positive. And then the kicker, the one that always, I think, not always, makes me scratch my head, often makes me scratch my head, is the shear force. So we'll do that again in red. And this one, it's either like, it's not just positive y. Okay. When it's open and open to the right and we have the left part remaining, this situation over here, okay, then we define v as positive when it's down. And then if it's exposing this way, all right, then we define the v as positive when it's up. So this is kind of Hibbler's convention. Okay, and why this is confusing to me is because when I took this course, we used a book called Crandall-Dahl, and you've seen references to it, CDL. Crandall-Dahl-Lardner, 1999, they use the opposite. Okay, so I'm teaching this class, I'm like, this just seems backwards to me. And it turns out it was backwards to me because I had learned it the other way. Okay, so those are just some notes on conventions. There are other conventions we'll get to pretty much right now when it comes to thinking about distributed load on an element. Okay, so first, let's just make a note. This is actually a multiple thing. It's not just about distributed loads. This is going to be distributed load, shear force, and moment. And these are all internal. Well, actually, nope. It's the shear force and the bending moment, those are internal, but the distributed load is typically external. Okay, so how do I put this? I'll say distributed load that's going to be external, while shear force are internal. Okay. So what we're going to attempt to do, I told you at the beginning of the class, there was a spoiler. Okay, we said that we're going to relate transverse shear forces and distributed loads. Okay, and we're going to relate bending moments and shear forces through these relationships. We're now about to derive these relationships. Okay, and the way to derive these relationships is by taking a slice. So let's say we have a beam. With a distributed load. Okay. So that's a crummy looking slice. And we're going to select a portion of this slice. And on this slice, there's going to be a distributed load. Okay. So just a note on distributed loads. I don't like them. They're real. They're real. Okay. Gravity is real, and thus is a distributed load. Okay. But it ends up often being confusing. Okay. So, but my fear, or not fear, my distaste with distributed loads should not influence you. The units are typically, when you see the W or the omega, the W, okay, that's typically going to have units of force per length. Okay. And so, you know, if it's a constant load, right, a constant load, okay, actually, this is often given like by a W naught, right? Then you have something like that, okay? And so over a given length, okay, you can calculate the effective right, is just going to be, let's call given length X, okay, is just that, right? It's just the W naught X. And if you're interested in where the effective moment is being applied, right? That's going to be given by this 1/2 W naught X squared, right? So you have W naught X, and then it's applied halfway, X over 2, and so you have the 1/2 W naught X squared. Okay. So you've seen this before. By convention, the way Hibbler does this, and this is not necessarily how other people do it, but the math ends up working the same, is that if you have this distributed load facing up, okay, this is positive. Okay, so now let's get to the actual proof, or to the example here. Whew. Oh wow, time flew today for me, not for you probably. But okay, so let's take a look at this element, and what we have here is a width delta X. And on the left side, okay, well, actually, let's say that this is we're going to call this point O on the right side. Okay, so that we'll use this point O as kind of our reference point when we want to do some moments. Okay, but we'll say on the left side, okay, we have a shear force, a moment, and yes, see, we're already using this convention right here. Okay. All right, and the other one for moment. So we have on the left side we have moment and V, and shear force. On the right side, we will have a V plus delta V, okay, just because we've gone over some amount, delta X. And then we'll also have an M plus delta M. Okay. And we can't forget that we have our distributed force. So let's first do summation of forces in the y direction. Okay. This is static equilibrium, so that sum should be equal to 0. So when we do this out, what do we have? We have a v here, we have a v, we have a v plus delta v, and we have a wx. So we end up having, and this, you know, this is helpful to see how this distributed load, whoops, that's annoying. I lost my, okay, see how W naught X, that's the force. So we had to equate that to these, or we had to balance this force from the Wx with the shear forces. So we have V in the positive minus V plus delta V in the negative, right? And then using our convention, we have like that. Okay. So the big V's cancel out. And what do we get? We get a minus, you can kind of see where this is going, minus delta V plus W of X times delta X is equal to 0. Delta V is equal to Wx delta X and delta V over X, or delta X, is equal to Wx. And then if we take the limit, as delta X goes to 0, we get dv dx, and this is equal to W of X. Okay. So that's the first relationship. So this first relationship is kind of important. So we'll put it here. In a box. Do you need to know this for Friday? Absolutely not. Okay. Should you know it for the next one? Absolutely yes. Okay, so how much time do we have? Okay, we got 4 minutes. Let's do the other side, and then we will have fulfilled our obligation to you to show that we know the relationship between these different transverse loads. So now we're going to do the moment at O, all right, some of the moments about O, and set that equal to 0. So if we do that, we get minus m plus delta m. Okay. And we're going to, this is a little bit tricky, but remember we said it was here, right? We said it will 1/2 W naught X squared. So here it's exactly what we do. We say it's going to be acting 1/2 the width of delta X times the force associated with it, and that's going to be equal to 0. Okay. So then this comes out to be minus m plus, or actually, sorry, the minus m and the plus m, they knock each other out, so we get delta m minus, oh, I forgot the v, blast. See, look, v is also acting, and that's going to be causing a minus v delta x. That's very important, because otherwise it doesn't work out. Okay, so delta m minus v delta x minus 1/2 wx delta x squared is equal to 0. The square of a small thing is an even smaller thing. So this component, this goes to 0. which means we get that delta M is equal to V delta X, and using similar logic to what we did before, the limit as delta X goes to 0 of delta M over delta X means that this is going to be dm dx, which is going to be equal to V. And this is the other equation that we're going to use in the future. Okay? So what did we do today? We did follow our obligation, okay, here. We didn't get to graphing. I'm sorry. I'll have to do that after the exam. Okay, but we did get to our relationships between shear force and distributed load, and transverse shear force and bending moments. Given that we didn't get to the graphing part, I don't think we should have an assignment before the exam. What do you all think? Yeah. So let's say there won't even be an assignment due next Tuesday. Okay. Besides the one, do the in-class assignment due tonight. All right. But we're good until after the exam. All right. Good luck studying. I have office hours today. TA has office hours tomorrow. We have group meet. We have email. Good luck. It's going to be okay. It's going to be okay. Have a good one. You too. Thanks.